And then you made like the connecting things like that.
Yeah, what do they call that? What's the
polygon?
Yeah, inscribe the polygon in the circle, point down. Okay.
Yeah.
So this is what they do: is they show a bunch of different frost circles to show you how it's done. I expect that you can be able to do it like on your own. That means you have to be able to draw a polygon in a circle. I won't make you trace your hand, and I won't make you color your name. Yeah. But you have to be able to do something like this. So we talked about what makes something aromatic and what makes something anti-aromatic, right? So aromatic. Look, white dog hair. This is my dog. What are the rules for aromaticity? They're called Huckel's rules. Yeah, nice. Flat. This is known as Huckel's first rule. Flat, and then fully conjugated. Okay. That means, the practical thing is, at every point it's sp2 hybridized. Okay. And it has to be fully conjugated, it has to be cyclic. So things, we only see aromatic compounds that are cyclic, all right, completely conjugated, sp2 hybridized all the way around. Second thing, odd number of electron pairs. There's this thing they call the Huckel number. So if you have one electron pair, which is an odd number, Huckel number's 2. If you have 2, the Huckel number's 4. It's the number of electrons in the system. I'm just telling you that because nobody knows what Huckel's number is. I mean, you're supposed to, but everybody just remembers an odd number of electron pairs. So that's the easy way to do it. Okay, so then we use the frost circle, anyways, to look at compounds like this, and this is when something is aromatic. Anti-aromatic means first rule obeyed. Okay, so this is the same rule. And then it has an even number of electron pairs. And then what we talked about is how molecular orbital theory shows us when something is aromatic or anti-aromatic, what the characteristics of something that is anti-aromatic. So for example, for benzene, the frost circle says the molecular orbitals look like this, or let's just draw it like this. And when you put the electrons in the system, it looks like this, right? All the bonding molecular orbitals are filled, right? No anti-bonding orbitals, no non-bonding orbitals are filled. When you look at something like cyclobutadiene, then you have to draw it like that. And if you draw the circle, that's pretty good. That's the frost circle. The orbital energy levels are like this. Okay. And then there's one more up here. There's 4 electrons, so you go 1, 2, 3, 4. Remember, these are what we call the non-bonding orbitals. This is anti-bonding, and this is bonding. And the thing about anti-aromatic compounds is they generally fill the bonding orbitals, but they also fill the non-bonding orbitals. And what it does is it gives, because the electrons are in separate orbitals here, they behave like radicals. Individual electrons, which are unpaired, and one of the things we know about unpaired electrons, just like from Chem 1A, unpaired electrons are a lot less stable. They prefer to be paired up. Okay, so that's the relationship of the frost circle to stability and instability. So we're going to go over some details. We're going to look at other systems that are aromatic or anti-aromatic. Those were the rules. Oh, and so there's 3 conditions, right? It's aromatic, it's more stable than you predict. There's anti-aromatic that's less stable than you predict. And then what's the other one? Non-aromatic, okay? So They refer to these as annulenes. This is known as a 6-annulene, that's benzene, okay? Aromatic, right? This is 10-annulene. Aromatic or not aromatic?
How do you describe that polygon?
Well, you can't.
So no frost circle.
Yeah, you could do a frost circle, but you have to, there's how many carbons on there, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You'd have to draw a decagon and then wouldn't work.
Well, it's fully conjugated, so
Fully conjugated, how many electron pairs?
5.
It's actually not aromatic.
Why not?
Yeah, good question, huh? What's here?
Carbon.
And then what's attached to it? Hydrogen and carbon, right? Where's this hydrogen? In the middle. Where's this hydrogen? In the middle. Can't both be there. In order to be fully conjugated, it has to be flat, right? But the hydrogens can't occupy the same space. So the ring actually twists at that point, right? And that causes it to be... it's not...
Are you recording?
I was until it stopped. Oh, sorry. I'll go back. Yeah, so this one, there's enough space, but how many electron pairs do you have? Oh, you get 7, right? So the hydrogens are far enough apart, they're just all next to each other inside of that structure, so that's aromatic. Okay. So it's a little bit tricky. There's not too many cases like this, so just remember, like on a 10-annulene, the hydrogens are too close, because they're pointed right at each other, and that causes that molecule to twist, okay? So it's just an oddball.
And because it twists, it doesn't keep it flat.
Yeah, in order to be continuously conjugated, this part of it, right, fully conjugated, requires that it to be flat. There is some degree of twisting probably in the 14-annulene, but it's not so great that it's not conjugated anymore. I don't know how you know that other than you saw this, and that's how you know it.
So is 14-annulene aromatic?
Yeah. So this one's not, just because, even though it seems to obey all the rules, these two hydrogens here, they're too close together, so it splits apart. Okay. So let's look at some other ring systems. I mean, we did some of this the other day, but let's look at some other ring systems. And the way I presented this is I said, okay, cyclopentadiene. Let's draw cyclopentadiene. Looks like this. And then I asked the question, aromatic, antiaromatic, non-aromatic. Aromatic, antiaromatic, non-aromatic. Non-aromatic because it's not continuously conjugated, so first rule, Huckel's rule, doesn't apply. Right? Then the question I asked is, can you make it aromatic? And what would you do to it to make it aromatic? No, without changing the carbon, just, yeah, make a negative charge, pull the hydrogen off, leave the lone pair. So you pull the hydrogen off, what happened to that? Sorry. How embarrassing. I just ran out of space. Okay. Put a lone pair and a negative charge. Then that is aromatic. But then you might be saying to yourself, but there's 4 groups on that carbon, right? Should be sp3. Right. The rule, yeah, right? Right. Now that you mentioned that. I wonder if I can, sorry. No, it's a different pen. This is a pen from the Happy, or the Friendly Swede online shop. So in this, the rule that we learned for resonance is if a lone pair can be involved in resonance, then we include it. So it does this. It forms resonance structures. And you can see there's a lot of different resonance structures you could make from that as you push the electron pair around. So if a lone pair can be involved in resonance, okay, then it will be. Then to refine that a little bit more, the refinement is if it can be included in resonance and is part of it and makes the system aromatic, then we always include it in drawing the resonance structures. Okay? If you include it and it makes it anti-aromatic, then we don't include it. Okay?
The resonance, if it makes it.
Yeah, if the lone pair and added to the system would make it anti-aromatic, then it's not included because that makes it even less stable. So it has less of a tendency to do that. Okay, so what kind of reagent would you use to make this happen? A base. Yeah, some kind of base, right? By the way, on the next slide, they show some of the resonance structures. Okay. And what we're talking about is you can use a strong base to remove, right, one of these hydrogens. Now, pKa's of alkanes, like sp3, right, carbons, the hydrogens attached to sp3 carbons, typically around 50, okay? This pKa is only 16. So that means it's a lot more acidic because when you pull the hydrogen off, it makes the system aromatic. So because the product of this reaction is a lot more stable, this hydrogen becomes a lot more acidic. Okay, it's easier to remove. All right, show you. So, okay, let me do this. So alkane pKa is typically around 50, right? It varies like 45 to 60. It's a big range. But they're basically all very weak acids, okay? So, but because removing the H makes the system aromatic, okay, right? It's a lot more acidic than you would predict it to be. Try something. Plug this in and see if that helps. I may have to reconnect here if it reroutes from a different network. All right. So here's the thing. Whether or not the lone pair that's involved is involved in making it aromatic or anti-aromatic affects the properties of lone pairs on molecules, okay? We talked about, I'm going to skip some. Okay, so here we go. Pyridine and Parole. Right. Pyridine, you guys know, we used it as a solvent, or we used it in solvents a lot. For what purpose? What's that? Deprotonate, yeah. We use it as a base, right? So pyridine acts as a base. Pyridine has a lone pair here. Parole has a lone pair as well. And depending on how you draw it, I think I'm going to draw it like this, has a lone pair there. What do you think about Parole? Pyridine's a base. What about Parole? Huh? well, the H is more acidic, but it's not really acidic. But as far as being a base, right? Pyridine has a lone pair, it acts as a base. Parole looks a lot like it, right? Has a lone pair. Is it going to act as a base? No, why?
It wants to become an aromatic.
Yeah, because that pair of electrons, if you include it in the resonance structure, right, makes the system aromatic. So that rule that I just said, like the modification, if the lone pair can be involved to make the system aromatic, then it's involved in the resonance structures. And as a result, this lone pair isn't available like it is in pyridine to act as a base, because it's involved in resonance, and it's kind of like me. I can only do one job at a time, right? So that lone pair, if it's involved in resonance and delocalization of these electrons to make the system aromatic, then it's not acting as it can't act as a base at the same time.
Can you repeat that one more time? I was just
I don't know.
ask you why it- and then you just said it, and I was like,
Oh, actually, I can do it from either slide if I can change slides. Okay, so the lone pair, right, on the parole is necessary to make it aromatic. Say necessary, it will be included in the Huckel number, right? But it means that lone pair, if it's involved in making it aromatic, can't also be involved in being a base. One thing at a time.
oh, okay.
It does one or the other. And then if you do protonate it, okay, then the system's no longer aromatic and becomes much less stable. Okay, so what that means is, as a base, right, it's very weak. If you protonate it as an acid, it's relatively strong because it really wants to spew that hydrogen off. That is, if you actually make this here, right, that is, you let parole act as a base, pKa is around 0.4. So the low pKa strong acid is very acidic. This, right, pK is 5.2, much less acidic because this lone pair is not involved in making the structure aromatic. This lone pair is involved in making the structure aromatic, so it prefers to be doing that job rather than being as a base.
What kind of acid would protonate?
What?
What kind of acid is that?
Would protonate that? You could do sulfuric acid.
Yeah.
Yeah, just a strong, just right, anything with a pKa less than 0.4 and generally not in water. Right. So HCl, HBr, H2SO4, bunch of them. Other evidence to show, oh yeah, so another way to talk about this pair of electrons is delocalized. This pair of electrons is not delocalized. And another way to show that difference between localization and delocalization is to do the molecular modeling and do the electrostatic potential map. And if you remember, the electrostatic potential map is a color map of the electron cloud around an atom. So you can look at, pyridine, right? And you notice the bright red here? The color scale is from blue to red, right? Green is neutral, blue is positive, red is negative. So red color means, what about electron density? High, and blue means low. Yeah, so that's what the map means. Electrostatic potential map. So if you look at pyridine, electrostatic potential map, bright red here, right? Electrons not delocalized. They stay in this part of the molecule. If you look at parole, you notice it's actually got a blue charge over here. Why does it have a blue charge over there? It's the formal charge of nitrogen when the electrons delocalize. So if you draw, let's see, sideways, like this, and you draw the resonance structure, It looks like that, right? So what I did was I took the pair of electrons, pushed it off to here, pushed that to there. You end up with negative electron density or high electron density over here, right? And then low electron density here. And the formal charge, it shows up as a positive charge on that atom. Okay? But that's the sign that the electrons have been delocalized into the system and making it, because of aromaticity, making it more stable. Now for pyridine, there's actually one other reason, and we talked about this actually last semester, so I'm going to go back. It's kind of like a review. There's another reason this pair isn't involved. What's that? It's sp2 hybridized already. This pair of electrons is in the plane of the molecule. In order to be involved in delocalization, it has to be in line with all the other p orbitals, and it can't do that when it's in the plane. So for delocalization, even though you have two pairs of electrons there that could delocalize, like look like they could delocalize, only one ever does in a system at a time. Okay? And that's just because of the geometry. Okay, so we're going to go over which of these will be aromatic, anti-aromatic, or non-aromatic. And we'll talk a little bit about whether or not the lone pairs are involved in the system. So just to make life easy, I'm going to call this A, B, C, and D. Just so I can call them by name. Unlike my children, when I forget when you're angry and you say, hey, you, and then they all respond. Yeah. So let's talk about A. Aromatic, anti-aromatic, non-aromatic. It's kind of a trick question, so you have to really think about like what the structure is. It's fully conjugated. Can this pair and that pair be involved? No, so it's got an even number. How many carbons in the ring? 8. Looks. Oh, sorry. How many atoms in the ring? Sorry. Yeah, 7. Trick question. Trick myself. Okay. What did cyclooctatetraene do? Do you remember?
I don't remember what it looked like.
Looks like a stop sign.
Oh.
It bends up, right? What does the bending up do? So if this was flat, it would be anti-aromatic.
Is that not
Bends
black?
up, but it just makes it non-aromatic.
It's non-aromatic because it folds. Okay. How do you know it folds? Because I told you last time. That's the only way. Right? Because being flat would make it anti-aromatic. The instability of being anti-aromatic causes the molecule to bend up. When it bends up, what happens is the p orbitals that are on the sides Well, okay, I can't draw. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Oh, went the wrong way. Like this. These guys fold up, and then what happens is the p orbitals that are along the sides can't line up properly. And that causes it to be non-aromatic. Okay? But if it was flat, you would guess anti-aromatic. So if I said this molecule is flat, it would be anti-aromatic. Okay, let's look at B. Aromatic, anti-aromatic, or non-aromatic? Okay, it's only 7 atoms now, I think. 1, 2, 3, 4, 5, 6, 7. Yeah, 7. So it can't fold like 8 can. Okay, so first question is what? Is it flat and fully conjugated? No.
Why is it not full?
See this oxygen here, right? The rule is now that pair of electrons is involved if it makes the system aromatic. If it makes it anti-aromatic, it's not involved.
Wait, say that one more time?
If this electron pair is included in the system and it makes it aromatic, then we include it because it makes it more stable when it's aromatic. If you include the pair and then including that pair makes it anti-aromatic, right? Makes it less stable, then it doesn't do that. In that case, these two electrons are both localized, and this is sp3 hybridized.
So then it's just non-aromatic then?
So then, again, it's like the first one. It's non-aromatic. This is sp3. Because including pair, I got to write really slow, otherwise it doesn't keep up. And I'm going to draw that instead of write lone pair. Makes it anti-aromatic. I'm just going to write anti. Okay? So you don't include it. Okay. That big thing.
It looks like the other ones that were aromatic. Just
It-
because pi bonds all around, it just have the one spot where there's the delocalized.
It delocalized, right? And so if that pair is included, you have 4 pairs in the ring already. If you include that, and just I don't know why they did this. I would have done that instead. But yeah, make it doesn't matter what it is. If it has a lone pair on there and it can include it, it would include it. It's continuously conjugated at that point because this becomes sp2. And it does that because then you would have 2, 4, 6, 8, 10 electrons, or 5 pairs of electrons. That's a Huckel number. Okay? Makes it aromatic. So this one's aromatic. And again, the inclusion of the lone pair happens because it makes it aromatic. Now what about D? Yeah, so if flattening out makes it aromatic, then it'll flatten out. The 8 bends, right? Cyclooctatetraene bends because it becomes anti-aromatic, and being flat makes it less stable. So again, it's this whole, why does it do it? It's folding because that's more stable than being flat. This is flattening out because that's more stable than being folded.
So we should assume first that it's going to be flat, and then if we find out that it's going to be anti-aromatic,
Then it's not.
It's going to bend.
Yeah, and that's only 8 atoms or up. 7, it doesn't have that flexibility. And the other thing about this is, because these rings, they get so big, right? As they bend, the angle between the p orbitals doesn't change that much. So it can bend. Actually, these can bend a little bit and still be aromatic. So we're looking at some what? I did? Not aromatic. Oh, there. Let's see. Let's count, right? It looks continuously conjugated. It has this 1, 2, 3, 4, 5, 6, 7, 8, 9. My guess is, I don't know for sure, it's not going to be flat because being flat makes it anti-aromatic, so it'll fold up to be non-aromatic. But I'm not sure it can do that. I'm pretty sure it probably does. How's that for an answer? That's a very non-committed answer. The one way to tell is to simulate it, do the electrostatic potential map, and see where the electrons actually go to. So if that positive charge is evenly distributed in the ring, then it would actually be aromatic or anti-aromatic. Okay, so let's talk about polycyclic. Believe it or not, my first introduction to polycyclic aromatic hydrocarbons, that's what these are called, and your first introduction to them. So polycyclic aromatic hydrocarbons. Your first introduction to them was in using heats of combustion. So you're going to ask the question, perhaps, when did I do heats of combustion of polycyclic aromatic hydrocarbons? The answer is when you barbecue. When you barbecue, it creates these polycyclic aromatic hydrocarbons. They're generally not good for you, okay? But you'll notice, how many electrons? 10, that's a Huckel number. 5 pairs, right? Here, 7. 7, 14, right, electrons, 7 pairs. That's a Huckel number. That's also a Huckel number. These are all aromatic compounds. So they call them polycyclic aromatic hydrocarbons. And we find them, like when you barbecue, you find them in all your food. And the only reason we barbecue really is because we apparently like the way they taste. I'm not sure. But they're not supposed to be good for you. I learned about it in grad school, and it was too late by then, so I figured, whatever. I will continue to burn my food. Okay. So if you wanted to measure the stability of these, you could actually do heats of hydrogenation and determine, like, stability of naphthalene, anthonine, and phenanthrene. And these are the kinds of numbers that you get. So for benzene, we talked about this number before, this 152 kilojoules. That is, if you take one double bond, hydrogenate it, 2 double bonds, hydrogenate it, and you extrapolate it to 3 double bonds, and you hydrogenate it, and you compare that to the heat of hydrogenation for benzene. The difference in energy, known as resonance, stabilization, or stabilization energy, is 152 kilojoules per mole. So it's that much more stable than you predict it to be. Naphthalene is 255. Right? Anthracene and phenanthrene are 347 and 381 kilojoules per ring. Right? That stabilization energy is a little bit lower than you have for benzene, but they're still a lot more stable than you predict them to be. So they have this quality that we call being aromatic, and we can use Huckel's rules to determine that they're aromatic because they still follow Huckel's rules. So for polycyclic aromatic hydrocarbons, to determine whether or not they're aromatic, you can apply Huckel's rules, just like we have in the past and like we did on that first slide, determine that they are. So back up for a second. Huckel's rules really only work well when you're trying to do polyaromatics, polycyclic aromatics that have 3 rings. So this is basically the end of the train. Okay. Beyond that, what you typically do is, honestly, beyond that, when you look at something and it looks like a bunch of benzene stuck together, you know in your head that it's aromatic. Okay? But what you can do, if you really want to, you can draw all the resonance structures, and if you can get benzene rings to show up in every single ring in the system, using resonance, then it's aromatic. Okay? So for things that are larger than 3 rings, you just have to fiddle with it and get it to go right. Okay, so the next thing we're going to sort of shift gears. We're going to talk about reactivity, okay, of benzene. But particularly we want to focus on what are known as the benzylic carbons. The benzylic carbons are these ones that are adjacent to a benzene ring. If you take benzene, just for instance, okay, and you try to react it with sodium dichromate and sulfuric acid, that's the Jones reagent that we talked about last time, right? No reaction. If you take alkanes and you try to react them with Jones reagent, you get no reaction. But if you take a benzylic carbon, right, and you subject it to Jones reagent, Jones oxidation, it converts it into a carboxylic acid. You don't need to know the mechanism, but the principal reason for that reaction to take place is that if you produce a radical at this position of the molecule, it's stabilized by resonance into the ring. So this position is very reactive simply because of the ring stabilization that it gets by being next to the ring. Okay? Aromatic stabilization. Okay, so you remember when you try to oxidize tertiary alcohols, right? Jones reagent, no reaction. Tertiary benzylic position, right? No reaction as well. Potassium permanganate can also do this, except for Permanganate, it's under basic conditions or not acidic conditions, and so you end up with benzoate ions. You end up with the anion for the benzoic acid, which you can protonate to get to the benzoic acid. Okay, other things cool about benzylic positions, bromination reactions using NBS or radical substitution reaction like Br2 and light, right? Prefer to react at the benzylic position simply because the radical is more stable, so it gets stabilization by delocalization into the ring. That mechanism you should know. Yeah, same as the lilic bromination, benzylic bromination is the exact same thing. And then, I'm not going to spend a lot of time on this, but I'll show it to you on another slide. Once you functionalize that position, right, then you can make all kinds of changes to it. You can do an SN1 substitution, produce an alcohol. You can do an SN2 substitution on primaries to form an alcohol. You can use a strong base. For example, with the benzylic halide, you use a strong base and very easily form an alkene or a double bond. So a lot of different things that can be done with this. And then once you have that, then you can add things to the double bond. You can do other substitutions, put different functional groups onto it. So a lot of different things. Your book sort of summarizes it like this. Right? Benzylic position, it can be oxidized if it's primary or secondary, right? As long as it has a hydrogen, if you just want to remember it that way. Then you can do bromination at the same position. You can also do bromination like this, and then you can do substitution or elimination reactions. Okay. So let's go through and give me the list of reagents that you need to do each of these transformations. And again, to make life easier, I'm going to call them A, B, C, and D. So how do you do A? Yeah, NBS. So you can do NBS and heat or some sort of initiator, but NBS and heat, let's say, or light. How do you go from B? How do you do B? What's that? Yeah, sodium methoxide, strong base, any strong base. These double bonds tend to form very easily. The first one does, simply because it's conjugated. The second one does because it's aromatic. Right? So this is aromatic, and because the product's aromatic, it's a lot more stable. Okay, so you can use any bulky strong base, or really any strong base. Oh yeah, right, it'll go the other way, potentially, yeah. So any strong base, though, because it's a tertiary alkyl halide, and elimination is going to be fast. And then what do you do for C? Jones reagent, yeah. Isn't that easier to say than potassium dichromate and sulfuric acid in water? And to get this from there, D. Same, Jones reagent. It doesn't matter what's here for Jones reagent. All that it matters is there's a benzylic carbon or a carbon adjacent to an aromatic ring and a hydrogen. And it chops everything else off. Right? Okay, some other things about reactivity of benzene rings and substituents to benzenes or reduction reactions. This is exothermic reaction. but it requires 100, so this is the hydrogenation of benzene to cyclohexane. It requires 100 atmospheres of hydrogen gas. Right? 100 atmospheres is a lot of pressure. The reason, even though it's an exothermic reaction, benzene is really stable. The energy required to break open the benzene ring and get it out of being aromatic is huge. Okay? Okay, so what this means, why is it exothermic?
It's the sigma bonds.
Yeah, you're forming sigma bonds. You're replacing pi bonds. Each pi bond is replaced by 2 sigma bonds. Okay. What this means, though, is if you have any double bonds attached to a benzene ring, right, it's very easy to hydrogenate it without affecting the benzene ring itself. And remember, anything that you can reduce with hydrogen or lithium aluminum hydride or any of those things can be used to react with substituents on a benzene ring and not affect the benzene ring. So, for example, reductions like this are possible. Oops. To form an alcohol, right? You can do hydrogenation to do that. You can use lithium aluminum hydride, and it doesn't affect the benzene ring because the benzene ring is so stable. You can even do this, which is a fun one. So nitrobenzene. To NH2 to make aniline. So you can take and reduce all the way down from nitrobenzene to aniline. And what we'll learn in later chapters is the properties of a nitro group and an amine group are very different. Nitro groups are strongly electron withdrawing, amine groups are strongly electron donating. And it'll cause us to be able to control a lot of what happens on the benzene ring during reactions. Okay. One of my, I don't know, favorite reactions? What does that mean? You should probably know the mechanism. Okay. One of my favorite reactions is the Birch reaction, just because it's an introduction to the importance of electron donating and electron withdrawing groups in reactions. Okay, so sodium, right, radical reaction. And remember, this is very stable. Sodium is very high in energy, so it's going to donate an electron. Donates an electron and forms an ion. This is the anion. When this electron is donated, the pi bond splits. One electron goes up, one electron goes over here to the side. Second electron comes over to the side from this pi bond, and then this last electron goes to the bottom, and you end up with a radical, and then these two parallel pi bonds. Okay? So this is known as a radical anion simply because it's a radical anion. Yeah. Very, very unstable, but you can put it in, you can have methanol as the solvent. And the side reaction will be that the methanol will react with the sodium too, but you have methanol as the solvent in this reaction, and it'll pick up the proton from the methanol. Let's see if the whole mechanism's on here. Yeah, picks up the proton from the methanol, and then a second equivalent, so second atom of sodium deposits an electron where the radical is, and then you get an anion which picks up a proton. And what you ended up doing is you ended up reducing in solution in a under fairly reasonable conditions, reducing a benzene ring. Okay. So final product looks like that. And then there's hydrogens at the top. One of the hydrogens was added, and a hydrogen at the bottom where one of the hydrogens was added. Okay. So an interesting thing happens. Oh, sorry. It gets sp3 at both ends, but interesting thing happens if you have a substituent on the ring. So if you have an R group that's electron donating, okay, you get this product and you don't see this product. If you, so this is a donating group. So what kind of things are electron donating, right? Methyl groups, ethyl groups, those kinds of things that have, by hyperconjugation, can donate electron into the benzene ring. You get that product. This product, it's not observed if this is donating because they're talking about being donating. This is the product you see if you have an electron withdrawing group. So the position of the double bonds, where they show up in the final product, changes depending on whether electrons are being donated to rings or withdrawn from the ring. Okay, so let's do this. I'm going to put a note down here. This is observed if R, that's too far down on the screen. If R is withdrawing. Real quick question. I've said what an R group is if it's donating. What's a withdrawing group? Highly electronegative atom, or like a carbonyl functional group. That's what we had in the Diels-Alder. You remember in Diels-Alder reaction when we had the dienophile. Right. Adding that functional group to the dienophile makes the reaction go a lot faster. That's an electron withdrawing group. So R could be simply that. Okay? So how do you answer that question? The easiest way to answer the question is look at the mechanism. Like the question is, oh yeah, what's the question? Why does it do that, right? So the easiest way to answer the question of why that happens is to look at the mechanism for the reaction. So I'm going to make a blank slide. I'm going to draw R as a donating group. So I'm going to substitute that as a CH3. Now, sodium could add to two different positions essentially, okay? Let's say the sodium adds here. Oh, sorry, adds to here. And then another one of these electrons goes that way, and that goes that way. Right? Then this bond is going to break like that, and then this bond's going to go like that. So that's the same as what we saw on the other screen, but we didn't have an R group on it, okay? That's what you end up with. The other possibility is just say it adds to the other side of the bond, okay? So I'm going to redraw this because there's so many arrows on here, it doesn't work to just draw them both on the same structure. I'll just call it ME. It's a little easier to draw ME in there. So that's if the sodium adds the electron to the position where the electron donating group is, okay? On the other hand, it could add to the other side of that same bond. Okay, these are some of the options that we have. So we have sodium. It adds here. So then this bond will break. Let's see if I can do this without screwing it up. I'm going to make my pen a little bit smaller, maybe. Not that that helps you guys any. So it'll go like this. Then this one's going to go the other way. And then what happens to the other bond is it splits again, like that, and then goes like this. So guys, can you follow the arrows at least? Right? There's a lot of them for every one of these. So then your structure can be this. Like that. So you get two different radical anions. You get different orientations of the double bond with respect to where the substituent is. Okay? Did you hand up? No? Okay. Which one of those, what's that?
Would it be safe to say that the radical and then the lone pair are para to each other in a benzene ring?
Yeah, they're para to each other. That's fair, yeah. But which one of those is more stable? Bottom one, because if it's an electron donating group, right, makes the anion unstable. So in the end, right, you're going to end up adding the hydrogen here and the hydrogen here. And the double bonds will be parallel to each other, but with the methyl group attached to this position. On the other hand, if it's an electron withdrawing group, and you end up with this, as the intermediate, right? Looks like a funny face. Sorry. Then by resonance, it's stabilized like this. Right? So what happens is just the effect of the electron donating withdrawing group controls the position where the radical anion shows up, where the anion portion of the radical anion shows up, and then controls the regiochemistry of the reaction. That is where the double bonds end up in the final product. Okay. So, example, right? This is your observed product when you have the electron withdrawing group. You need to be able to explain it by mechanism. So I want to know that you understand what the effect of the withdrawing and the donating group is on the final product outcome. Okay, a little bit of spectroscopy at the end. I like doing this more with pictures. There's a picture on the next page. We'll go over these real quickly. 3,000 to 3,100, okay? Between about 2750 and 3,000, you find hydrogen stretches, okay? You remember this? Hydrogen stretches. You guys have seen a lot of it in lab, and you guys probably did some lab last semester, some IR. So you get hydrogen stretches in that region, we say below 3,000. So just ballparking like a chart like this, we have percent over here, transmittance. There's 3,000, 2,000, 1,000. Then in this region here, it's all sp3 CH stretches. But if it's beyond that, then what we find is that it's beyond 3,000 in this 3,100 range. we normally attribute that stretch to the hydrogen that's on an sp2 carbon.
Is that why we call them alkene regions before?
Yeah. It's what we normally where we see alkenes. There'd be peaks like this here around. This is 3100. Right, that is in that range. You find peaks in that range that are sharp, but usually not that big. But if you usually find those peaks that are sharp in that region, those are sp2 attached, and that's because the sp2 orbital is shorter and makes the bond stronger. And this frequency, this higher number of frequencies, relates to bond strength. Okay, so they tend to be more sp2 attached here. If you just go beyond this region, we get alcohols, some OH groups and stuff. But you also get sp-attached hydrogens, like alkynes, triple bonds, where it stretches for CHs on triple bonds. Okay, now, from about 1700 to 2000, okay, I'm just going to show you this in a picture. You get what they call these combination overtone bands, or overtone bands. They look like this. So here's the in the 3000, 3100. This is the CH stretches that you would see on a benzene ring. So remember, I taught you guys last semester. Take your chart at 3000. Just draw a line. If there's stuff to the left, it's got double bonds in it. If there's stuff to the right, it's got single bonds, single bond carbons with hydrogens on it. So that's this part here. This part we don't do much with. Most of the time, it's obscured. Because even though it says there's not a lot of stuff there, if there's a big peak next to it, it's sometimes hard to see these peaks. Or these overtones, these are actually multiples of peaks that are down in this region, and they just happen to line up like this. These overtone bands are sometimes hard to see. But it turns out the pattern that you see, okay, tells you how many substituents are on the ring, and tells you their position on the ring. So this is what you expect to see when you have a single substituent on a benzene ring. Okay? But safe to say, right, even if you can't remember that, I'll give you the chart. Like you need it on test, I'll give you the chart that says, oh, look at these bands. That's what this means. Just look at these bands. Huh? No. So Nice try. I know. So I think I just pulled the top of my pen off. But I'll give you the chart. So you'll be able to look if you have a compound and it's got its ortho substituents. It has a very particular stretching pattern. One or two of those peaks is missing. I don't even remember what they are. I just have the chart and I flip open to it and I look at it and that's what it is in there. A couple other things. Again, these things get in the fingerprint region, get harder and harder to find. But 1450 to 1650, you get CH stretching, or CC stretching. You get in the 1000 to 1300 range, 1275. You have CH, what's called bending modes. No, actually, hang on. Yeah. So when you're analyzing your spectrum and you have a benzene ring, you expect to find some peaks in these regions here. There's in-plane bending. So like if I was a benzene ring, what would I be? What would my geometry? I'd be flat, right? So if these are my, so I'm not. I'm just saying. If I was benzene.
So you're not stable?
I'm not. I don't have abs of benzene. But there's in-plane. This is in-plane, and then there's out-of-plane bending. So those both have different bending frequencies. So that's what they're saying. The CH is bending is in-plane. CH is bending out-of-plane. Okay, that's what you expect to see. So in and out. So here's the thing. When you look at these, don't go, oh, look, I got that peak. That's benzene. Right? It's a bunch of peaks that you look for. Right? You look for combinations of all these peaks to tell you, this is, by the way, remember CC double bonds around 1600? That's pretty traditional. For like alkenes, we've seen that. For benzene, you'll see a peak here too because it's made up of CC double bonds. Okay. So don't try to identify benzene based on a single peak. Look for things that indicate that you have benzene. Most of the time in labs that we do, when you have benzene, you kind of know you have benzene. So really what you're doing is you're trying to verify other things that are attached to the benzene ring or the orientation of substituents, that kind of stuff. Proton NMR. Benzene typically falls, okay, so alkenes, right? Proton NMR, so hydrogens attached to alkenes, typically see in the 5 to 6 range. And you remember if you remember why that happens is when you have a double bond like this, it has p electrons like this. And so it makes a cloud. When you apply a magnetic field to it, let's say this is your magnetic field, right? Then what happens is the electrons in the cloud begin to circulate, and as a result, they produce a counter magnetic field, which then circulates through the molecule like this. It gets really complicated, but the simple thing to remember is, right, if you have a pi bond and you're next to it, you're shifted downfield. Okay, downfield to the left. So where a CH2 group is typically found around 1.4 parts per million, you might find it as high as 2.5 parts per million. That's about a 1 ppm shift for being next to the benzene ring. The reason the shift is so big is because in benzene you don't have just one pi bond, you have 3 pi bonds, and the whole benzene ring acts as this, the whole benzene ring acts to produce that counter magnetic field. So the magnetic field it produces is much larger. If you're a hydrogen on the benzene ring, the magnetic field generated by the ring causes an offset of between about 6.5 and 8. Okay, so for ethyl benzene, it says that it's 7. But where these things actually end up isn't dependent just on the fact that there's benzene here. There's electron withdrawing groups or electron donating groups. Electron withdrawing groups cause it to shift this way, electron donating groups make it shift that way. So that's why you expect to find hydrogens on benzene rings in a fairly large range of about 6.5 to 8. Okay.
So is it safe to say that it's the same trend that it goes next to an electronegative?
Yeah, just like being anywhere, like if you're next to an electronegative atom, you're shifted downfield. So if you have an electronegative atom, let's say it's here, right? Or electron withdrawing group, that's what an electronegative atom is doing. Electron withdrawing group here, these two that are next to it will be shifted further downfield. These will be less affected. But interestingly, the effect is bigger in the ortho and the para positions for the electron withdrawing groups and electron donating groups, and it's weaker in the meta position. Okay, so it's a little bit hard to sort of pick out, but also coupling. Remember we talking about like coupling is when you have like 2 groups next to each other, like this methylamine group and this methyl group. They're next to each other. Right, 2 hydrogens produces 3 peaks or 3 peaks here, and then 3 hydrogens here produces 4 peaks here. Same thing happens on the benzene ring. So this is coupled to this, right? This is coupled. It's also coupled to that, though. That's the trick. In alkanes, right? The coupling is usually just the neighboring carbon, right? But for aromatic systems, because they're all tied together by the electron cloud, the coupling is the strongest ortho, it's weaker in meta, it's almost non-existent in the para. So then what happens is, when you look at the signal for this hydrogen, it's coupled to both of these but differently. So you end up with sets of peaks that overlap on top of each other a lot. We'll spend time in lab analyzing that stuff.
So those are always multiplicity.
Yeah, when you see the multiplicity of the peak, and I might have time actually to explain it a little bit better. That's more a lab kind of thing, but I can explain it here just as well.
Because a lot of times you see peaks that are
what you're saying, we have like equal amounts and like one larger in the middle depending on how many
Yeah.
hydrogens there are, but that would cause different levels of peaks, right?
Yeah, and it,
Like that,
like that, yeah.
and staggered.
Yeah, so there's a bunch of peaks, they're all on top of each other. They're all coupling ortho, meta, and not really para, and they're all coupling different amounts. There's no electron withdrawing, no electron donating groups, so they're all piled on top of each other. If I had put an electron withdrawing group here, like I was talking about here, these two peaks would have been shifted away from these, and you can tell, right, that what they are. You can actually see their multiplicities on the NMR spectrum. Okay, honestly, if you have like a $2 million, $3 million NMR, yeah, then you can see it just when it's like that too. Yeah, we don't get to do that. Couple of the really useful proton signals that you can see. Okay, again, around 7 parts per million, but it depends on what the groups are. So this is the start, and I'll do more of this in the next chapter. When you have electron donating, electron withdrawing groups, if they're the same, okay, if it's X and X, these hydrogens are all equivalent. And so rather than seeing a bunch of splitting peaks, it produces one signal. So if by symmetry they're exactly the same on the ring, they reduce down to a single signal and you don't see the coupling. So you'll get 4 hydrogens on a single peak that way. If you have two groups that are different and they vary in their strength for electron withdrawing or electron donating, then these H's will be the same with respect to each other, and these blue H's will be the same with respect to each other, but they're different than the one next to them. So what ends up happening is hydrogen, this blue hydrogen, will split this red hydrogen into 2 peaks, because it has one neighbor, and this red hydrogen will split this blue hydrogen into 2 peaks, because there's one neighbor. And what you end up getting is a doublet of doublets. You get 2 doublets next to each other. So this is the pattern that you see when the two groups are opposite each other, para to each other on the ring. So some of you who are doing the lab right now and already got your NMR, you're going, wait, that's the NMR I saw in my product. Well, that's your product. It's para, yeah. Ortho and meta are harder to analyze, but they're just as easy to spot. Like to go through the process of figuring what the peaks are, they're just as easy to spot without a lot of detailed analysis. Carbon NMR is the best if you like simple. And we combine this with depth, and that makes it even simpler, right? 2 signals for carbon NMR from this structure because of the symmetry. It's got a plane of symmetry this way and a plane of symmetry this way. So this one, and these are 2 groups that are the same, right? If those 2 groups are different, and it's in the para position, then you end up with 4 signals. Because the top and bottom, there's a plane of symmetry going this way. If you have 2 groups that are the same and they're next to each other, you get 3. If you have 2 groups that are each other and they're meta to each other, you get 4 signals. So if you have xylene as your starting material for any experiment that will remain unnamed, which happens to be this current experiment, and you do the carbon NMR, these are the xylenes that you have. Okay. 4 signals for the ring. 1, 2, 3 signals for the ring. 4 signals for the ring. 2 signals for the ring. Plus the non-ring atoms as well. Okay, so the rings are the starting materials are very easy to identify based on if their xylenes or 2 groups are the same, very easy to identify based on the number of carbons you see in the aromatic ring.
Are the 2 substituents the same or different?
The same.
Then why would it not be a 4 signal if those 2 are different?
Wait. These are different.
No, top one. Nope, up a little bit. Right there.
That one.
Why is that one?
4?
4 signals.
Oh, there's 2 different groups, and there's one symmetry this way. Right? But if we're talking about xylene, or there's a couple of methoxy ones, there's a couple of starting materials that look like this. It follows the same pattern. You'll be able to identify the starting ring positions just based on the number of aromatic ring signals you see. Questions other than that? So let me hand out the sheet of paper. We got a little bit of time. We didn't do this last time because I got distracted. 1 minute essay. That would be something. One question each, please. Or 2 questions each. I'm still going to sort it down to just a few answers. Then I don't have to count them, and when you're done, I know you're so good you'll collect them all up anyways.
Who printed out slides?
Huh?
Who printed out slides?
Oh, I did accidentally. That is, it's a buckyball. It's named, this class of compounds, they're named as fullerenes. Fullerenes. The guy who came up with the concept of this shape and its stability was known as Buckminster Fuller. So this is known as Buckminster fullerene. It's the molecule named after the dude. What's that?
Is that what you made last semester? When you made the ball?
I was trying to make that, yeah, but I didn't have enough carbons. What's cool about Buckminster fullerene is it's a C60 sphere, interlocking hexagons and pentagons. But if you notice, it's continuously conjugated. There's no hydrogens on it. And because it's so big, all the p orbitals remain conjugated to each other, and it's aromatic. So these compounds are extremely stable. The Nobel Prize was given out for graphenes this year, I think. This is in that same class of compounds. They're super cool. They were discovered basically, I don't know, 15 years ago. Well, yeah, you can put stuff inside. One of the really cool applications of this is to try to do modifications on the outside, and then you can actually, if you fire a metal ion towards it, it'll trap it on the inside. Okay, so this sounds kind of like crazy. Why would you want to do that? On the outside, you can put antibodies on the outside, and then you can introduce that into somebody's body, and the antibodies could attach to, let's say, a tumor. And then the metal ion, what they do with it is they irradiate it at the right frequency, and then it generates radiation that kills the tumor. Yeah, that's like a cool reason why you want to do it. Another reason